Hello, SOS 232 folks. Hopefully you're doing well. As you can see, I'm trying to integrate some technology and getting my face associated with the slides so you don't just see the recordings. I hope you're doing well. I know that last module was intense and a lot, but I think that we can power through. If you are having questions, if you're still feeling a little bit delayed, don't fret too much. More focus on the the material that we're seeing and being adapted. Come to office hours, come to tutoring, put in that work. Ask me email questions, ideally Monday, so then by Tuesday I can answer them and help alleviate those things. As a reminder, that time management situation, that's why we have those little surveys every module, makes things make more sense. So I'm hoping you all are feeling okay with this stuff. And if not, you're reaching out to me to ask these questions. Um, as a small note, September has been an interesting turn of events. This module and these lectures were kind of devised under before all of September has happened. So there might be questions that have some fervor to it, but I urge you all to think about these things in a statistical data science, social researcher element. And we're going to try to distract because one of the questions deals with gun control, and it's an issue right now. We're going to sort of treat it as a social science researcher instead of having that sort of political, philosophical opinion and just seeing where those viewpoints might fall in line. So, just as a sort of beginning of video heads up that we talk about those things, but I want to make sure that that makes sense. All right, let's begin. So, in the previous module, we talked about proportions and using chi-square and trying to find those relationships where they exist. But now we want to look into, how do I compare means? What does that mean for us? In the PowerPoint presentation, we'll talk about ANOVA, analysis of variance statistics, and they're a test that deals with a numerical and a categorical variable, also a comparison of means. And we'll look into ANOVA in general, the definition and running ANOVA, and eventually our F-test, some estimation and comparisons, as well as an interpretation and write-ups that you all have done kind of throughout the course. We're just going to do it with this flavor. I'm also adding a little bit extra, and this is kind of adding some padding to the quiz and whatnot. We look some further notes on social statistics, basically the social statistics beyond surveys. So kind of go beyond what would you do beyond this point, because we're getting near the end of the course in terms of module information. And we'll have a small discussion on ethics, because I think, especially when we start talking about ANOVA, there is something called, dealing with experimentation. And we get some folks that are just, they're social science researchers, but they might be social science researchers who have elements that might also be reflected in psychology, in public health, in nursing, or other public policy. And there might be ways to deal with things that are sort of experiment focused to keep that in mind. So it's good repetition. Tests of statistical significance allow us to determine whether our findings are generalizable to the population. They allow us to answer a main question: how confident can we be that the relationships we're observing in our sample data reflect something broader and generalizable to the population? It's a huge question, you all. In Module 4, you explored relationships where the variables are both categorical. We looked and saw how those contingency tables overlapped with each other, and seeing what those percentages might look like and how they may change from one group to another using those column percentages. Module 6, next module, we're going to look into relationships with two numerical variables to then basically do something that explores something we call regression. But right now, we're going to ease into exploring relationships a little bit more, now using a numerical variable and a categorical variable. So not two of the same, but actually two different ones. and we'll do so through the ANOVA F test. Now, the ANOVA F test is a test of statistical significance that subsequently should only be used when working with data that's representative of a population that's under investigation. It's a test of significance that deals with a numerical and a categorical data value. That is, when working with the categorical continuous variables and testing the relationships between those variables, we can use the ANOVA test to determine whether or not we could be confident about generalizing the findings we observed in the data of the population as a whole. So, kind of going into a reflection of representation in our populations, if we don't think that this stuff is actually as representative as we'd like it to be, that could be a hiccup, could be a problem. We want to explore that issue because if we can't generalize it to a population from our sample, the data we probably have might be kind of garbage. We want to deal with that too. So keep all those things in mind that we want to have a relationship in our investigation between what we got from our survey results to the actual population at large. Now I'm going to use the term ANOVA. ANOVA is not scary. Again, we're saying these words, and if you read them, yeah, it's probably not the most comfortable because you're like, these are weird math terms and they're awful. That's why I recommend doing the lecture videos, listening, and now I got a little bit of a lecture thing where I can actually see my face as I'm talking about these things. These are just unique terms in the same way there are unique terms in sociology, in psychology, in nursing, and public health, and social work, etc. And so I'm going to talk about those things, and you don't have to know the very fancy ways that this stuff works. And that's the whole point. Like, I'm not trying to make you go very technical. If you want to go technical, and some of you all, this might be, ooh, this is kind of cool. I want to do this more. I recommend talking to the stats department, talking to other departments, maybe do things that are more quantitative focused and say, hey, where should I explore next that kind of gives me a little bit of the inside outs of this stuff? But for right now, we're kind of just sort of trying to go with vibes on the terms. And when I say analysis of variance, ANOVA, all it means is we're trying to explain or analyze why our numerical variable varies the way that it does. Why is our numerical variable varying or changing or shifting, or why do you see those breaks the way that we kind of see that it is? Is it due to just the randomness of it all, just like how maybe age varies? Or could it be explained by something else? Some other variable. Right now, we'll talk about it in terms of categorical variables. This ANOVA exploration actually allows us to compare means of each category or each subgroup to see if there is evidence that a difference actually exists in these means. And if, in effect, usually tries to explain that there's a difference in these populations. So when I look at certain groups based on a numerical variable, that we think that these groups have unique population structures that are different from group to group, or at least between two of those groups. Now, we may have some differences in the output, and we're going to talk about those things, but keep in mind the same process we've been doing falls into the bigger picture here when we interpret it. We talk about our propositions and some notes of hypotheses and explanations of the alternative hypotheses, the because. We'll talk about some of the descriptive statistics, and we'll are adding a little piece at the end. We'll talk about it after the first sort of set of quiz questions. We'll also talk about significant test results and then discussions of future research. This should feel pretty similar to what we did last module, and a little bit on the module before that when we sort of left it with some practical differences. We talked about contingency tables. So note It's the same song, but we're changing a few words and it's a new cover. But it's really still trying to figure out how do we talk about relationships between two variables? Only now, both of them aren't categorical, only one of them. Now, ANOVA is calculated by doing some computations, numerical descriptions, and I have this table provided. That's the mathy formula. Don't stress too much about that, other than if you have a number of groups, we'll call them K groups, and we have the number total of all the people. These formulas would go through and would find what we call an F statistic or an F test. This F value, kind of like chi-square, and really all it is, this measure basically is a measure that takes how much variability is happening from group to group compared to how much variability is within each group. So if I'm looking at something like age, and I want to say, does age seem to vary from people who have a or people who are in a lower class, working class, upper class, middle class structure? There may be. So there might be that the age is very different between middle class folks and working class folks. And there also might be differences in age within each of these groups so that not everybody is the same age in the middle class. What we'd like to see, if we think that it's actually your social class that has an impact, then there's more variability happening if I shift from working class to middle class than if I just are looking inside the middle class group as a whole. So the F statistic helps measure that and sort of says, hopefully, ideally, that there's more variability if we jump from one group to another group than how much variability there are in each of the groups respectively. But don't worry too much. ANOVA actually, while a lot of computers will compute it out, Jamovi will do all the work for us. You're never going to be calculating this stuff by hand. You're just going to have to see the results and be able to interpret it and report on it in a scientific, sophisticated manner, which you're all still developing, but you're getting there. You're doing well. So now we just have to learn how to set up our ANOVA test, and then we can interpret our results. This requires that we talk about setting our significance levels again. And significant levels, really, just like when we talk about chi-square and now with ANOVA, we just got to set this up to determine whether or not we can reject the null hypothesis and determine whether a relationship is statistically significant. As a good reminder, our goal is that we're researchers. We have research ideas and we're trying to prove we are right and the ideal, the null hypothesis, that nothing is related. We're trying to prove that wrong. So significance level is basically if we were to claim that we were right, in fact, we screwed up, it's not true. How comfortable are we being okay being wrong? In a similar vein, at the courtroom trial example, we talked about how, what are the chances that we basically are sending an innocent person to jail? We don't want to send an innocent person to jail. We don't want to claim that they're guilty. So we don't want to screw up very often. So our significance level is basically an error level of sorts. We want that error to be low. We can't get 0 because we don't necessarily have the entire population, but we can hopefully get it to where it's like 5%, 1%, 10%, something like that. There are 3 levels of significance we talked about. There are others, and really there's nothing special about them. These are just ones you might see as standards. And each level of significance comes with a corresponding p-value that sort of represents when we can actually reject or fail to reject. So the typical values for significance level, the one we'll use most often is going to be 0.05, where if no relationship actually existed, the chances of us accidentally, just by the way we collect data that happens, sometimes we're unlucky, We collected data, and that showed a relationship that actually isn't there. And that could happen. So at the 5% significance level, that's where, you know, we accidentally get those values. So in our goal, our p-value that is also reported, we want p-values that are less than or equal to, no more than 0.05, because that's our 5% significance level. 1% significance levels have less of a chance of making this error, but we accidentally get more of a chance of not detecting relationships when they actually do exist. So it is okay to be more strict about not screwing those things up, but we may miss out on other things. So there is a trade-off that does happen. So a goal of statistical significance, the 1% significance level, usually less than or equal to 0.01. At the 10% significance level, there's like bigger error. So that is a hiccup, but we actually have more of a chance of detecting those relationships if ones do exist. So if we're trying to do those things, we're not worried about whether or not we're wrong. So maybe an advertisement that changes every 6 months, that might be something that is not as stressful about being wrong about these things. So it's all about the context. 5% is a great start off point, and then you can talk about those things with your fellow researchers and also look at the consequences that may be going along with those things. So we'll go ahead and we'll do some GSS work, and we'll basically look at the same thing we did last module of, do you require a person to obtain a police permit before they could buy a gun? Now, before using a statistical test of significance, you got to set up your propositions. This isn't anything new. You did this before, like last module. Basically, does education level, degree, matter in explaining one's position on gun control? That's what you did in module 4. These are two categorical variables, and you can look at it that way. The new example is, does age, a numerical variable, matter in explaining one's position on gun control, or the categorical variable of measurement? And there's a small hiccup. Technically, I can't lie to you all. Trying to say that does a categorical variable get explained by the numerical variable, basically, is y being categorical and x being numerical. That's not what ANOVA typically does. There's a very fancy type of analysis, or different types of analysis. It's a little bit beyond the scope of this course. It's called like logistic regression or other forms of things. I don't want to go too much into that because it's not worth it at this level. If you go advanced, you're good. For now, don't stress. However, one of the things we talked about last time is that association actually goes both ways. If I want as a causal component, that one thing causes another, I couldn't necessarily get away with this. It doesn't really work that way, and I would not feel comfortable. However, if I'm talking about just association and just talking about relationships and not trying to worry that we have a causal component here, I can get sneaky. I can go through and say, all right, I can use ANOVA to prove or to show that age gets impacted by whether gun control, the changes in age that we observe, seems to be impacted by gun control. That whether someone is opposing or in favor of it, the age variable seems to change. So if age is associated to the gun control, I can flip it and say gun control is also associated to age. So we'll still use ANOVA on this to test associations, but we're going to be sneaky about it because ANOVA is a big picture item. It's good for you all to see it and know it, but it's not doing exactly what we're claiming, but it does give us the equivalent results because association goes both ways. All right, hiccup over. We'll do kind of the stuff we did before. Note, It's just these sort of steps. Step one, put it in this symbolic form. Is Y related to X? So is gun control related to age? State your hypotheses. What's more likely? I'm going to try to make a claim. I don't even know. I don't know. I'm believing these things. The data might prove otherwise, but this is my reasoning why I think there's a relationship. And I think that probably older Americans will actually be more likely to oppose stricter gun control because older Americans might be more likely to support Second Amendment rights to bear arms. And so that whole gun control debate, we've seen conversations about this over the past decades. Always require that that because statement because we want to sort of explain where the theory is. Don't say I, don't use that personal I, but talk about things that you've seen that may have been viewed in data analysis or explanations before. And then always state the null hypothesis in your when you're writing up these things, and that there's no relationship between X and Y because it reinforces that we're not. I am not necessarily trying to prove anything. I would like to prove something. That would be great. But I can't say that there is a relationship if the data doesn't really show it. I'd have to do something else and try to prove it in another way. Resample, resurvey, wait till next year, or so on. But I'll go with the objective idea. There's no difference in individuals, older or younger, whatever. There's no age difference really on average with the position in gun control. There's one more step in setting your propositions. Basically, you're setting your level of significance. And for this class, like I've said before, if I only use 5% level of significance the entire time, no problems. If you want to try to go a little bit fancier and go with the 1% or go with the 5 or the 10%, we'll allow it. There's no problem with that. Ideally, stick with 5%. Don't overexert unless you really want to go the extra mile. I'm not making you. We're not trying to do that. We're really just trying to build those foundations. And that means basically is that if no relationship is actually happening, then whatever when we are collecting our survey data and doing an analysis, then that data collection process, we collect data, and just by the randomness and kind of chances that we could be unlucky, and then we just got a weird combination of people that show that there is a relationship, and we would incorrectly suggest an association exists when there actually isn't one. Basically, we get unlucky and find a false association when there's no actual relationship. We just accidentally found it. That 5% significance level, that's where that's coming from. So it's our error rate. So now I'll test those propositions. What statistical tests we use? Well, gun control is categorical. Age is numerical. So we'll use ANOVA, this analysis of variance test, to test that relationship. ANOVA tests, they're pretty rad. There's certain rules for writing results, and we're going to explore those things over the next few slides. We'll make sure when we use the one-way ANOVA to go to age as our dependent variable. Now, as I said, I'm actually wanting gun law to be the dependent one. That's the ideal. That's our Y. But ANOVA doesn't do it that way. So we have to, be the sneaky switch gears and then convert back at the end. We'll put the categorical variable into the grouping one. And then for the descriptive tables, make sure the descriptive tables and descriptive plots are checked. And we'll talk about those things over the course of this module on what they can give us and how we can analyze them. You'll get something like this for the descriptive tables. So it gives us this table that, not the ANOVA table in full, it actually gives us a really quick summary of a one-way ANOVA, this Welch's ANOVA. And we'll talk about the plots soon, but we'll focus on these tables for right now. Mainly that we can report the means, the respective standard deviations, the sample sizes, this SE we'll talk about soon, for age, the average age for people who favor gun laws or oppose the gun control laws. As well as this F statistic, these DFs that we're going to talk about, and our p-value. So how do I interpret it? Part one. In your descriptives table, circle the cells where you expect your mean to be higher or lower depending on your hypotheses. Compare the means across those categories to determine whether you have support for your hypotheses. So, in fact, we have a hiccup, honestly. We kind of thought that folks in general, the ones who were opposing gun control would be older. And in fact, it looks like it's younger, at least in the 2012 data. It's a little fascinating. I'm surprised too. Don't stress too much if you have reverses, because as a good reminder, I'm trying to give some pre existing information and thinking why we're getting these things. But honestly, we're looking for associations, relationships. That's all we're really looking for. So if we flip the script on accident in this course, as long as there is a relationship, we're not going to stress too much about which direction it is, whether we're right or wrong. It doesn't screw up our overall understanding. And because if even if it's in the other direction, there's still a relationship that exists. Now, when you talk about the ANOVA results, you're going to actually now be 4 values. Before there were 3 for chi-square, where we had a chi-square, the degrees of freedom, and your p. Now, actually, there's a df1 and df2. df1 actually relates to that between variation, degrees of freedom. And df2 relates to the within all these groups. And I'm going to be real with you all. There are formulas that I provided for you. This Welch's is actually a different one that's a little bit different than the ANOVA table that I gave you all. There's many different ANOVA tables and tests, and it's going to depend on which situation you have. We'll use what's called the Welch's ANOVA, which is a little bit different than what you saw earlier, but it's useful with our data varies wildly among groups. There's a lot of variation. The F value basically is what we calculate based on the formula results, and that gets us an F value of 11.1. The df1 is our numerator degrees of freedom, but we'll just call it df1. It's basically a measure for the number of groups we have and we're comparing. So it's usually the number of groups minus 1 in this case. So because I had 2 groups, favor and oppose, then I can go through and say, all right, 2 groups minus 1, 2 minus 1 is 1. Yeah. And so in that situation, we can go through and we say that there are 1 degree of freedom, and we can power through. And then we go to this denominator degrees of freedom. And for right now, it's really a great way to say it's related to the measurement, the size of the sample gathered. It also has a relationship to the degrees of freedom 1. But right now, it's a great way to think about, like, if I see a really huge df2, it's probably that we have a pretty big sample size. Then we have the p-value. The p-value is basically the probability that relationships can't be given over to chance occurrences and basically statistically significant. We talked about this before with chi-square. We have it here. And so the rules to apply in our example, we'd write it out as such. We'd have, there's your F equals 11.1. Degrees of freedom 1 is 1. df2 is 599. P-value, I wrote that it's less than 0.001, and so I'll just put it there as less than that. If I don't have that less than, I just say it's equal to that value. This is really tiny, and I've mentioned before, we're going to reject almost all the darn time. And in fact, we can definitely reject because it's less than 0.05. And even though it's in the opposite direction, my bad, if it's in the opposite direction, it doesn't necessarily mean it is wrong, because really all we're testing for is a relationship, and we try to give some explanation, even if we were a little bit off. So if I'm writing this up, we propose that older Americans would be more likely to oppose gun control laws than younger Americans because they're more likely to be favorable to the Second Amendment. You say, a comparison of means, however, suggests that this shows the relationship may be the opposite. Those favor gun control measures average older, so the mean is equal to 48.9 years, and those in opposition, mean is equal to 45.3 years. And this difference is statistically significant. So F is equal to 11.1, DF1 is 1, DF2 is 599, P is less than or equal to 0.001. It's totally okay to switch gears in a direction because our main goal is to determine association. It's almost saying like, we're just trying to find something that's related. I thought it was one way. It's actually the other, but it's at least there is a relationship. And that's important to pull out. So how do I write up these results? I'm going to remind you all, don't get overwhelmed with this write-up. We covered all these things, this paragraph, we covered all of them already, only bit by bit. And when you read the paragraph, go back to the previous slide and see where we plucked the lines from. Well, now I'm going to pull them all together along with potential future scientific research so you can get to theorize some and use your social science know-how to talk about what you think this actually is meaning. So we also wish to explore whether age is associated with one's position on gun control. One reason behind the suspicion that older Americans may be more likely to support gun control laws and be more favorable toward the Second Amendment principles to bear arms. A comparison of means, however, suggested that it shows that the relationship may be the opposite. Those in favor of gun control measures on average older mean than those in opposition. And this difference is statistically significant. While these findings report on 2012 data, it might be interesting to look at this relationship on 2025, given the growing number of gun incidences. So those changes that talks about future research to explore what will be going on. Always review the writing research, rules for writing research in this module and all the others. Carefully review the rules for reporting ANOVA results. And you're going to be doing this stuff for your blogs and homework, so make sure to read this stuff. If you're not reading it, you're harming your own chances of understanding what's going on and seeing these examples in real time. Likewise, there'll be a Jamovi short video on getting the ANOVA results and testing for statistical significance. So make sure to utilize that to actually analyze what's going on. Now, evaluating differences practically. I'm only going to talk about this very briefly, but we could also talk about them practically, and we'll do so through the histogram density plot. So using those as descriptive statistics. And we can go to exploration descriptive tasks that we did in module 2. So nothing new there. And we can add the age variable as our numerical variable. But we'll also split by gun law, and it'll break it up into two separate groups. By splitting it into those separate groups, those differences may also depend on standard deviations and whatnot. So we can then break it up to those groups, but it's really, sometimes it's difficult to detect it by the naked eye. We'll be using the histogram density plots as well as the box plot provided. And you get something that looks like this. I can see that with age, there is a little bit of a differences. It looks like it's like a lump here. And then it has like a lot of folks who maybe are younger, and then differences in the folks here. And so you see a little bit of a change in these distributions. The box plots, I see a shift upward. By the naked eye, it almost looks like it's almost the same. And that is difficult, right? Like, how do I determine from this in practical differences? I don't know, but I would. And that, I think, is why there is some slightly big issue. I think the histogram density plots actually show these distinctions, these differences a little bit more and how it seems to be distributed differently. The box plots might not. So here is where like I see a slight shift, and a shift of 3 years is probably something to be notable. But it also will depend on the people involved. So if we see major differences, it's like if I see a major difference and the ANOVA F test is probably going to give us the same results, and we have significant differences. If we don't see a major difference, it may depend on the researcher what actually means by practical differences. The box plot, I don't know. I think it tells us something, but it doesn't tell us a lot. I see a little bit of a jump, but you have to like put on the glasses for that. This, I see a difference. I see some breakdowns a little bit more. And so we're going to avoid practical differences for beyond comparing means in this course, because I think it's a little bit goes beyond the easy foundational cookie cutter way of explaining. A higher level data analysis, data mining course would be cool. But we're not going to worry about that. So, but I wanted to talk about it as ways to explore. All right, take a short break. We went through a lot of stuff already. Test your knowledge. We have some quiz questions. See what you learned so far. Make sure that you are doing well so you can go through the motions and feel good to go. All right. You back? We good? Cool. So there are many groups. So if we have a bunch of groups, where would the differences be? Now, just like when we examine frequencies and proportions through chi-square tests, we have statistical relationships between two variables, but maybe not all categories or all groups may actually be different. If we only have two groups, well, then yeah, we can compare the two groups. But if we have three groups and we see there's a relationship, is it between group 1 and 2 that there's a difference? Group 2 and 3? Or groups 1 and 3? Or all three of them different? I don't know. So this is where this section is going to sort of talk about those pieces. So just like when we examine these chi-square tests, we have statistical relationship between two variables, and not all categories or groups may be different. So, for example, marijuana legalization, like we talked about in our practice problem, an additional problem. It isn't much difference between the lower and upper classes. The lower class of percentages were 55 to 44, 55 to 44. It's almost identical. It was wild that we had that. But it happens sometimes. It's a weird case where, yeah, it looks like we have the same thing going on. And so in that case, I don't think there's a difference here. I think the real difference, but there may be a difference between the lower class and the middle class. Or even, there might even be a difference between upper class and working classes. But there are distinctions, it just may not be all the groups. Module 4, we relied on the practical differences to help determine which groups were distinct. But in this module, we're actually going to look at something else, at comparisons, by introducing a concept called a confidence interval. And then, very honestly, in translating some of the stuff, sometimes you see the typo where I accidentally put confidence instead of significance. I try to fix them. My apologies. But confidence intervals and significance tests actually will go hand in hand often. If you go into a more stats class, they may actually spend weeks on those things. In this class, we're going to just briefly talk about it and utilize it as a tool to help determine those differences and those distinctions, and use it at a visual level, which is really nice for others to easily interpret. This measure adds what we call reliability to our estimates of means. In general, when we perform a statistical inference, no matter what we're doing, it involves producing an estimate like a mean or proportion, and it's based on our survey sample. But like we said before, when we make an estimate, we want to know how reliable it is. If I were to go through and do another survey, grabbing another group of people as a subsection of our population, we may actually get different results. So this mean, this proportion, could vary from survey to survey, even if it's the same goal during the same time. Statistics is a science because it can state how reliable the estimate is as opposed to just pulling through a specific value. So this measure of reliability is a statement, it's usually quantified, about the degree of uncertainty associated with a statistical inference. So for example, if someone says Kodak estimates the battery lifetime for a certain type of battery, it's about 7 hours plus or minus 20 minutes. So if I were to claim that, we would expect the battery would last typically between 6 hours and 40 minutes and 7 hours and 20 minutes. So we have that reliability beyond just a specific number. So it's not saying, oh, I only got 6 hours and 52 minutes. This is false advertising. Well, adding that level of reliability says, okay, we think it's this, but we could be off by a little bit, but we think we can bound how off we are by these values. When I talked about the descriptive tables, I said this SE thing we'll talk about later. Now we're here. We get our list of sample sizes in, means, standard deviations. This column, these SEs, are known what's called the standard error, which is a measure of reliability for our sample means that helps basically tell us how much our mean might change if we were to do this survey over and over and over again. For this mean, for our sample mean, it's actually, I'm going to say this in a way that's kind of whispery. So it's not the standard deviation of age in general, but the standard deviation of these sort of sample means. That if I were to do this over and over again, don't worry too much, is basically saying this reliability, how much of an error could be off on typically from the 48.9. Sometimes a run through a survey's data collections might be sampling folks where the stuff is way off. It is the sacrifice we get for not getting everyone. If we didn't do this, if we didn't have that situation, that could be a problem. But the problem shouldn't happen very often if our results are solid, and we can use this standard error, this SE, to get a good, reliable idea of the true population means, proportions, whatever we're trying to measure, what it would be. So a confidence interval then becomes this range of possible values that we suspect our true population measure to be. This range of values is based on our survey sample's mean, standard deviation, the SD, not the SD value here, the number of people responding, and also about how confident we are, which is known as basically our confidence level. This confidence level ranging to at most 100%, so 0% is not confident at all, 100% would be perfectly confident, but not really viable. It's how successful this method is going to be at getting the true population value. So there is this procedure, this confidence interval. This confidence level says this procedure will be successful at doing its darn job about this percent of time, and that's why we're confident in it, because this is our success rate. So, and one of the nice rules that come from this is if you have a mean, an approximate 95% confidence interval for our means are going to be within about basically two of these SEs, these standard errors associated with it. So if I were to say the mean is 49.8, the standard error is 0.561, then a 95% confidence interval would be about 47.778 years and 50.00 or 022 years. And you know how I found that? I put it into a calculator. That would be the most you'd have to do, but honestly, this is me sort of telling you about these things without you having to do them too much, but if you see them again, you know what to do. So in a way, you could describe this as basically we're 95% confident that we weren't unlucky in our data collection, that we, randomness hits us fast at life, but we weren't unlucky. And because whatever our population mean is, we don't know it exactly. We have a good estimate based on our sample. But whatever our population mean is, our sample data says that if we were unlucky, then we're screwed. But if we were fine, if we got lucky enough, and we should be lucky enough 95% of the time, then when we collected our data, the sample data based on means, their deviation, and so on, the average age for those who favor gun control should be between it's somewhere between 47.778 and 50.022 years old. Anything in there is fair game because we don't know. We only got sample data, but this is our bounds of where we think the population should be, which is a pretty good way to shrink it down. People usually are between 0 and 120 years old, and at whatever the average is, it does seem to be restricted on the idea that it should be about nearly 48 years to about 50 years. Now in Jamovi, I had you all click on this descriptive plots thing, and it gives you an image of these 95% confidence intervals for each group. That's what this is. This is the range, this 95% confidence interval range for each of the specific groups. You will never have to, I'm not requiring you to calculate anything by hand for this piece. One of the reasons is that different levels of confidence actually people may want different confidence levels. So we won't go too beyond that part, but we'll put the 95% confidence intervals. And we'll compare these things visually to see if where differences may exist. So whatever two differences, if there is a difference, that means this range of values wouldn't overlap. So it all overlaps around 48. 48 could be the true value here, could be the true value here, could be the true value here. Because these are possible true values, I don't know if there's a difference. Any of these values could be fair game. So if there is a chance that they all could line up, I don't want to risk to say that there's a difference. If there's an overlap, I consider not to be a difference. If I can see that there is a gap, in worst case scenario, take a screenshot, put a square or something or a rectangle like what I just did, and see, can I put two rectangles that don't overlap? If I can do that, that means that there isn't an overlap, which means there is a gap or a space that I could be wrong on either way with this level of reliability. But based on this reliability, I'm still not seeing an overlap. So I feel comfortable saying that there's a difference in means that exist. And look, this is the gun law one. So, it looks like there is a gap, which we saw. We saw statistical significance. There would be a difference. And based on this piece, it looked like that people who are in favor are older, and it is distinctively older. So how would I write this stuff into my results? This feels like a whole other level of writing. It seems like a lot of work. Not too much. In fact, we only have to add 3 components. The first component is we add that SE to our line when we talk about the means. So basically saying those in favor of gun control measures on average were older. So 48, we said the mean is 48.9 years. Standard error is 0.561, so basically a half of a year. And we'll let others calculate those confidence intervals how they see fit. They maybe want to be 99% confident. They may want to be only 90% confident. They may want to be 99.9% confident. We'll let other people do that. By reporting the standard error, we're going to basically run on the idea of that 5% situation. And we won't worry too much about the rest because if someone wants to do it differently, we provided them the information to calculate that on their own. We'll also add the confidence interval plots that you use to write up for the others. So that way they can visualize and see what you're describing. And then we'll add a line that describes the difference if one exists. You can say that one doesn't exist. That's okay too. But if there one exists, basically there's a higher age means something's older. And if there are multiple groups, more than 2, don't feel obligated to report on everything. No, if there are groups that are higher or lower, notice one or notice some. That this is distinctly higher than this one. Compare 2 groups that are distinct, and you can mention that. And that alone tells us why there is an association. So based on this information, based on our 95% confidence intervals, the favors group age is on average higher than those on the opposed group. That's all we have to add. Putting this all together, note in red is all I added, plus I added this plot. This plot right here, plus the things in red. That added a whole, 10, 12 words? That's it. I wrote the same thing as I did in part 1, only I added a little bit extra to give us more information that our table also told us. And sorry about that. And I added a simple word phrasing that based on our 95% confidence intervals, the favors group is on average higher than the opposed group. That's it. So don't get too overwhelmed. It's just another piece of the puzzle. You got this. All right, take a short break. We kind of did all the statsy things we're going to do in terms of major numbers things. And now we're just going to talk about concepts. It's an extra piece. Feel free to test your knowledge, what you learned so far, and let that mood chill for a second. Do some practice problems, feel comfortable, all those things. All right, ready? Here we go. We're going to end here on further notes on social statistics because we did a lot of things with ANOVA, testing for association, but there's some additional things in social statistics that are important to check out. That there are things like analyses that complement survey research and ethical concerns to keep an eye on. For those who are maybe beyond, the social sciences, maybe nursing or public health, you may be doing things like experiments. In social work, there might be other surveys, there might be interviews that go alongside these things. So the next few slides, when you want to look at research, it kind of delves into that. And just like how I talked about how everything is sort of interconnected and we can explore these things, social science and social research isn't just about data. I'm a data fan. I love me some numbers, do some number crunching, talk about it like a number cruncher would. But it's not the whole end thing. And so we want to talk about how these things intertwine because that's important too. So while survey responses and statistical analyses go with them also provide a lot of valuable information about society views, there's some limitations to statistics alone. Often, quantitative research methods like surveys benefit from the inclusion of qualitative research methods like interviews to help explain the story behind these results. Remember, data, if I don't ask a specific question that has an easy yes or no or a certain categorical explanation, it's not going to be something that can be pulled very easily for our analysis. Open responses can do something similar to that, but it's still not the same level of patterns. So if I'm trying to speculate why things might be happening or certain behaviors, interviews and other qualitative research also probably fits the mold a little bit better. In fact, I'm going to add a separate piece right now. This blend of research is known as mixed methods research. And it's pretty darn useful if I do say so myself. Now, the other side, trying to describe causation is really tricky with only surveys, and even interviews may not provide that situation. Conducting scientific experiments, especially if you're starting to lead into social science that also can be natural science oriented, like public health, like nursing, or even psychology, can be dealing with experiments controlled for certain factors to make it easier to produce a cause for why we see these differences. So some cautions about interviews, basically, and experiments. While interviews and other qualitative methods can be quite informative, it helps paint those stories beyond just data analysis. There's still often anecdotal evidence. You can't get 500,000 interviews maybe to explain those things as well as you could do maybe 500,000 data points. So they're best merged alongside discussing the statistical patterns or relationships that you find within surveys. At times, there's an accidental unconscious bias by the practitioner that skews the effects. Having well-trained interviewers or to hide the treatment types from the practitioner helps mitigate those biases. The placebo effect may also occur in experiments. It's the response, and it is the response of the patient to any treatment, even a dummy treatment, because the trust of the doctor and expectations of the cure. So, I think this thing is supposed to help. This medication is supposed to help me with sleeping. I sleep better because I think this medication is doing its job, but it's really just a sugar pill. And maybe I'm having a sugar crash, and maybe that's why I'm sleeping. But it could be something else, but this is just a placebo. It's not actually sleep aid. So we have to be cautious and controlled for such effects of what just happens when you take a placebo. As a reminder, there's a difference between statistical significance and practical significance, which we've sort of been exploring. So keep that in mind. Even though there is a statistical significance element that we want to have, if there aren't practical significances, especially in these large survey research situations, we may find something insignificant, but it is not necessarily meaningful. One potential problem with experiments, sometimes if you do a very fancy experiment, there's a lack of realism. So like people aren't actually acting like this. Surveys help really kind of talk about real world. Experiments may have a lot of constraints that aren't going to happen in the real world. So it limits our ability to apply these conclusions when we want them to. Some other problems include refusals, non-adherers, dropouts. So why do they drop out? When you lose people or they don't do things, that does mess with the results. So keep that in mind. We'll finish up with this idea of conversations on statistical ethics. So we talked about producing our survey, research data, interviews, experiments. But how ethical is the research we're conducting? The concept of statistical ethics is incredibly important, even within research studies, because you're going to navigate your research and results that fit the restrictions that sort of maintain our humanity. We're going to finish this model by discussing some of these restrictions, along with some examples, some funny, some really messed up. But I want to talk about these things because you all are about to go into a very human world. And those human worlds have these restrictions compared to maybe something that talks about corn production or something. That's a different situation. But we're going to talk about the sea where these ethics and statistics fall into place. Oh no, it's showing up. I'll move out of the way. Unethical points. Some obvious examples of unethical statistical practices are things like telemarketers who begin a sales pitch, which I'm conducting a survey. Really, they're trying to scam you. There's also researchers who fake their data for publications, and that's an issue. It happens more often than we hope it would. Apparently hasn't prevented numerous instances of data fabrication. In 2016, Science Magazine actually found about 1 in 5 surveys had fraudulent data in there. It was really messy, and we're like, ooh. We also might get misleading news headlines, which promote scientific findings, especially on non-humans, based on research conducted on humans or non-animals. James Heathers in 2019, I think he was at Northwestern, I think that sounds right, in Chicago, created the now defunct Twitter account, Just Saying Mice, which was really, I had fun with it as a nerd. To debunk some of the news clickbait claims, noting how they just are results found in mice. So, like, they talked about could eating garlic reduce age-related memory problems? Ooh, that sounds fancy. The reality, they gave something an element, a chemical element, this sort of oral allyl sulfide, things that are in garlic, to mice that were like 22 months or 2 years old. They basically gave it to mice where they thought that this fits the situation between 56 and 69 years. And they compared this with mice younger than that who didn't receive this supplement. So it has kind of elements of eating eating something that garlic has in it improves memory with mice. Are you mice or man? We're humans. So this may not mean anything. And it's a little bit of a substance that may not mean much, but it feels very clickbaity. And that's worthwhile to critically analyze and call out when you see it. Some basic rules of statistical ethics in general. Let's see if I can just fix these things. Statistical ethics in general kind of fall into these 3 realms. One, we want to say these, everything basically dealing with these complex issues. We want to have what we call an institutional review board. It's charged with protecting the safety and the well-being of the subjects. All individuals who are subject in a study must give their informed consent before data is collected. and all individual data must be kept confidential. Only statistical summaries for groups of subjects could be made public. So you don't want to actually have the bigger data that comes through there because that gets a little messy. The most complex issues happen when we have people and animals because they usually will spring from, and they especially when they spring from experiments because they impose treatment on people as opposed to just a survey research. Your survey results have importance, and there are notes to keep in mind, especially with questionnaire design. But if you're going into experiments, this is going to be a big issue to keep ahead of. So in general, institutional review boards, it sounds like a fancy thing, and it is. It's important if you're doing a lot of research, even on campus. It's not necessarily whether or not it's statistically worthwhile, like you're doing good stats, but it's about protecting human rights. So the Institutional Review Board, EKU, usually these things, like you submit a proposal of what you're planning to do, and they have to consider all these things, and if they approve, then you can do your research. Sometimes these IRBs might falter, especially if workload increases. Duke University in 1999 got overloaded and they started accepting things that shouldn't have been accepted and they were not ethically sound and got caught and everything got shut down. They lost funding for a good minute and that was a mess. So they try to do well. If they're not, then they need to be called out. When it comes to confidentiality, it's important to protect the subject's privacy. Confidentiality refers to the agreement between the researcher, interviewer, and the participant of how data will be managed and used. Note that this isn't the same as anonymity. Anonymity is basically, I'm the person who's responding. You don't know anything about me. I'm just giving you my responses. You have nothing about my personal information. It is ideal to have confidentiality, and that's kind of separating you have my identity, you know who I am, but you don't really know what my responses are, and I'm kept private. So if it's confidential, then I have the opportunity to be more honest about things I might do. And so, especially when you're dealing with risky questions, having that confidentiality gives a level of privacy and protects individuals. And as opposed to anonymity, where I don't know you, I can't follow up with you if you're anonymous. But if it's confidential, then I can actually pull up your information and get a follow up later on if needed. The best practice is to separate the subject's identities from the rest of the data as soon as possible. And that helps work with that situation. Last piece is with informed consent. So even with survey data, the participant needs to be made aware of the nature of the study and the research in order to give informed consent. Informed and consent are both necessary. Subjects must be informed in advance of the nature of the study and the associated risks, especially if you have like clinical trials or something like that. And also, they need to be able to the researchers tell the respondents in full of the nature and purpose of the study. The subjects must give consent in writing. These issues can involve when subjects are not capable of informed consent, or researchers regard consent as a barrier to get the patients to participate in the research. Maybe a little bit less in terms of survey stuff, but it's still important to keep those things in mind. So not laying out possible risks, being too optimistic, or have very long consent forms. How many of you all have had those contracts from AT&T or something, and you've skimmed through, but maybe didn't read everything? That's kind of that situation. Also be aware that there's something called, there's possible coercion, or basically obtaining a compliance from explicit or implicit threat of harm. So if you don't respond to the survey, you may not get promoted at work. That's an issue. But on the flip side, there's also something called undue influence, which means obtaining informed consent through an offer of excessive or inappropriate award. So like, example, prison inmates were once used to test new vaccines, and they would be given their consent in return for good behavior credit. This reward puts folks in danger and leads to murky ethical waters. The ethical principles of the American Psychological Association require consent unless a study merely observes behavior in a public place. If I'm observing things, then that's not a big deal. It's observational research. I'm not causing anything, so it just pulls it up. Survey data can be fairly safe as well, so not too much of an issue, but if there is this sense of deception, it's only necessary for the study, It doesn't hide information that might influence the subject's willingness to participate and is explained to the subject as soon as possible. So, I'm saying these things, and for social science research, it may not be an issue. But this stuff is you think of things that are wild, but like this stuff happens. And so I'm giving you a couple examples of some that are hilariously messed up and some that are like really messed up. And this is what we considered as science and social science research and research in general for a number of years before we were like, look, y'all, there is an ethical guideline that we need to hold. So I'm going to explain some of these and talk about them because I think it's important as social science researchers, as statistical researchers, and whatever you're going to be doing, to keep in mind that there is a history of people doing some shady stuff, y'all. So for one, psychologists wish to study whether violations of personal space have physical as well as emotional effects. They decided to formulate their study in a men's public restroom and blocked off urinals to force men walking in to use either a urinal next to the experimenter, the treatment group, or a urinal separated from the experimenter, control group. Another experimenter, using a periscope from a toilet stall, measured how long the subject took to start urinating and how long he continued. What the ever living heck? Published in 1976, not even 50 years ago. This was in the Journal of Personality and Social Psychology. And people weren't informed. This is so messed up. So messed up. And why, like, no one would consider this ethical at this point. This is a private space issue. 100%. Second one. In the 1960s, children entering Willowbrook State School, an institution for the intellectually disabled, were deliberately infected with hepatitis. Yeah. The researchers argued that almost all children in the institution were quickly becoming infected anyway, so just go ahead and stick them with hepatitis. The study showed for the first time that two strains of hepatitis existed. So in the 1960s, we learned by infecting children with intellectual disabilities, just shooting them up with hepatitis and learning, oh, look, there's actually more than one strain. I think there's like 7 strains now. I think we've learned that at this point. The findings contribute to the development of effective vaccines. The Willowbrook studies are now considered an example of unethical research. I wonder why people would do this stuff. And even with the consent of parents, this is messed up. I personally do not care that they thought that, oh, it's going to happen anyway. You are infecting children with an active virus to see how those viruses attack the children. That's messed up. And the other last one we're going to talk about, which is a serious component that is important to keep in mind, that this is less than 100 years old. In the 1930s, syphilis was common among Black men in the rural South, a group that had almost no access to medical care. The Public Health Service Tuskegee study recruited 399 poor Black sharecroppers with syphilis and 201 of them without the disease in order to observe how syphilis progressed when no treatment was given. This is in the 30s it started. In 1943, they realized penicillin actually was effective antibiotic and became available to treat syphilis. The study subjects were not treated. In fact, the Public Health Service prevented any treatment until word leaked out and forced an end to the study in the 1970s, which means these men were not told that this actually treated their syphilis and were left to suffer the complications of being infected with syphilis until someone leaked and told them, you all are not being treated intentionally. The Tuskegee study is an extreme example of investigators allowing their own interests and ignoring the well-being of their subjects. A 1996 review said it come to symbolize racism in medicine, ethical misconduct in human research, paternalism by physicians, and government abuse by vulnerable people. In 1997, President Clinton formally apologized for the surviving participants in a White House ceremony. The research design stuff is probably fewer risks involved other than like if research data, if they say like, give some survey answers that are a little bit not legal, there's a worry about that getting caught. But like if you go beyond the idea of survey research, keep in mind that there are a plethora of things to consider and ethical guidelines to uphold so that you all are making sure that you are helping others. So keep in mind with those things, folks, because that is important as you become researchers in whatever field you go into. All right. The last batch of questions are more concepts based on this sort of ideas list, statsy. So test them whenever you feel like. And that's it. Good luck. You got this. Keep going. We're almost to the finish line. And I'll talk to you soon. Later, folks.